Welcome, everyone. Welcome to the Robofest Online World Championship RoboMed event for 2021. Welcome, spectators. We have spectators joining us via the live stream, but you can also join us on the Zoom webinar. If you would like to switch to the Zoom webinar, you can get the link in a recent post. We have a feature for spectators. If they would like to ask a question to one of the teams, you can type it in the chat. And then after the event, we will summarize them and then send them to the teams. And then the team's answers will be sent back to judges for final consideration. So spectators, please be aware of that. This is our schedule today. We've had our official check-in. We're going to have some opening ceremonies and then proceed right to the presentations. And then winners of all the categories will be announced on the day of the closing ceremonies, October 2nd. All teams have gone through the check-in process. Thank you very much. Robofest is a program of Lawrence Technological University. We thank them very much for their support.
Hold on,
We also thank our
Elmer.
Yeah.
Let me show the video right now.
Okay, let's do that first. Okay.
Sorry.
Warm greetings and good health to the world from Robofest and Lawrence Technological University. Welcome to the Robofest 2021 Online World Championship. I am Virendra Modgil, President and CEO of Lawrence Technological University in Southfield, Michigan, USA. STEM education, which is science, technology, engineering, and mathematics, and computer science, are the focus of RoboFest competitions. Students are challenged to integrate problem solving, teamwork, creativity, communication, and the arts into projects. Success at RoboFest requires mastery of multiple STEM and computer science subjects, which in turn drives preparation for college, classes, and high-tech careers. We learned last year during the complete shutdown of in-person competitions due to the coronavirus pandemic that we all could successfully conduct a competition-based learning environment completely online. This year, our 22nd RoboFest season, there are a variety of online, in-person, and hybrid competitions based on the conditions on ground in each community. We will all continue to learn, adapt, and deliver LTU RoboFest competitions for many seasons to come. I commend all the participants, teams, students here being active learners and pioneers who are eager to master technologies for the future. Thank you for your participation in this competition. Lawrence Technological University, as you may know, was founded in 1932 with the support of automotive pioneer Henry Ford. At that time, Ford's famous Model T factory was at the forefront of an industrial revolution that changed the world. Likewise, we are at such a forefront of new technologies, such as artificial intelligence and autonomous vehicles. Lawrence Technological University and RoboFest are paving the way. Someday, I hope you will join us here at Lawrence Tech to continue to do the excellent work you are already doing through LTU's RoboFest competition. Your efforts are advancing science and technology for solving real-world problems. There are many people who make RoboFest possible. I would like to thank them all, the teachers, the coaches, mentors, parents, volunteers, location judges, LTU judges, site hosts, and all the inspirational international directors who have organized local qualifying competitions or are sending teams here to RoboFest 2021 Online Championship. In closing, I wish all of you luck with your endeavors today and hope you have a great learning and collaboration experience through the online RoboFest 2021 World Championship competition.
Thank you, Dr. Modgill. And thanks again to Lawrence Technological University for their support. And thank you to all our others, our sponsors for this year, which are shown right here. Thank you very much for your support. My name is Elmer Santos. I am the RoboFest Assistant Director. Also with us today are Shannon Polonis, RoboFest Coordinator, and Pam Sparks, RoboFest Coordinator, and Dr. CJ Chung, the founder of RoboFest. RoboMed is one of several World Championship events. Please join us for some of the other events that are coming up in the next few weeks. Today, we have 3 college RoboMed teams and 1 senior team. Thank you so much for joining us today. It looks like there's some very interesting projects and looking forward to viewing them. Next up, I would like to introduce the judges for today. So Shannon, how should we do this? You want to spotlight each judge and then we'll do the introduction? Okay,
I can do that.
thank you.
Who's first?
Let's start with Dr. Jiang.
Oh, hello. Hello, everyone. My name is Hao Jiang. I'm an assistant professor at Department of Biomedical Engineering at Lawrence Tech. Thank you for joining this contest. And I'm pretty sure like you found like lots of things you're doing have a lot to do with our biomedical engineering curriculum. And I wish we can see your talents and your skills continue to shine at Lawrence Tech in the possible future. Thank you.
Thank you. Next up, we have Dr. Lee.
Hello, everybody. My name is Yawen Li. I'm also teach in Lawrence Tech in biomedical engineering as well. And this is my 2nd year being judged for RoboMed. And in the past, I also judged for the exhibition. And I used to also coach a robotic team and participating in the Robofest game. So yeah, it's been wonderful. On either side of the Robofest, and really look forward to hearing your great presentations today. Thank you.
Thank you. And lastly, we have engineer David Carberry.
Good day. My name is David Carberry. I graduated from Lawrence Tech with a degree in electrical engineering in 1989. Since then, I've been working with industrial robots at Fanuc Robotics. I currently work in the product development group. I've coached and judged for several years at Robofest, and I'm looking forward to today's presentations.
Thank you. Next up, I would like to go over the judging process and how we determine winners. Teams are required to provide videos as well as source code. Code inspectors will review the code for points and scoring. Judges have been selected by Lawrence Technological University RoboFest office. Their bios are available on our website. For the actual live competition today, the host will give the microphone to each team, and then each team will have 4 minutes to present and demonstrate their robots. Afterwards, there will be a 2-minute question and answer period. Teams must use English for all communications. Judges' questions may be translated at the local level when teams do not understand. However, answers must be directly in English. Judges may ask additional questions by email within 24 hours after the competition, and then teams have 24 hours to respond. Okay, I think we're up to the point for the group photo.
All right.
So can everyone turn on their cameras, please?
Okay, there's a nice view here. Let's see, Mechs Attack. If we could see your team, and Aerobots, if we could see your teams. Oh, there we go. Yep, kneel down there. Want to see your faces. Dr. Jang, could you also show us your face? We'd like to get everybody's live images. There he is. All right, thanks everybody. 1, 2, 3. Oh, and let me get another one. All right, very impressive group. Thank you. We're good.
All right, thank you. Okay, we're at the point for the presentations. So the way this will work, we will spotlight your video, and then we, when you're ready, we will start the timer. Okay, so let's see. First up is Aerobots.
All right, I'm moving the other two teams to the panelist side. So all we have are the Aerobots with us. So the team and the judges are the only group. I'm going to turn off my video.
Okay.
And on the video for the timer.
Con la presentation. No estamos muteados, nada más que aviso.
And when you are ready to start, I will start the timer. Just go ahead and start your presentation. And I will start when you are.
Okay, you want me to handle the spotlighting?
Yes, if you could do that, that'd be good.
Okay.
Okay. Yes, we are ready.
Whenever you're ready, you may begin.
Okay. Yeah. Hi, I am Toño, and he's David, and we are Aerobots Robotics from Toluca, Mexico, QID 2895-2. And we are going to present to you baby breedings. But first, some data. Every year, around the world, 2 million babies are born, from which 200,000 babies will be premature. Because of this condition, they will need oxygen therapy. Oxygen therapy is a treatment that consists in supplying a specific quantity of oxygen that the baby needs. This treatment is not always effective in phase 1 and phase 2 due to the following factors. First, the unpredictable behavior of the premature. Second, the high workload of the medical staff. And third, the oxygen is manually adjusted by the medical staff. This can lead to respiratory, cognitive, and visual disorders. Now, let's talk about our prototype. In this table, you can see the progress we made since last year's competition. And now, David is going to explain to you this in more detail.
Now, at your left view, you can see an exploded view of the current prototype. At your right side, you can see the monitoring model. At the center, we have the FPGA controller that has been useful for signal conditioning. And at the left side, you can see the oxygen control model. Now you will see how baby breathing works. First, considering that the baby arrives in a critical condition, the device will increase the oxygen quantity supplied to 100% of VO2. And now Tonio will be the test guy. First, he will connect an oximeter in order to get the oxygen saturation measurements. That is the most important measurement for the oxygen therapy protocols. With the same device, we can also get the heart rate. As a second sensor, we have an ECG model in order to get the respiratory frequency of the patient. Both of these frequencies are important to detect if the patient is making an extra effort to keep well oxygenated. And as a complement, we have the temperature model to have a complete view of the patient diagnosis. Now, as you can see, as Tonio has a well oxygen saturation of 95, 94, the device was decreasing the oxygen flow in steps of 5%. Now you will see what happened if Tonio has a sudden desaturation. the device will increase again to 100% of oxygen flow. As you can see, now Tonio has again a well oxygen saturation, and the device continues to decrease the oxygen flow in the same step. And now you will see what will happen if Tonio has a little desaturation. Immediately, the device increases the steps in 5% of oxygen flow. All of this behavior is expected during the whole treatment. And also, we included a report generation model in order to get a complete view of the patient response to the treatment. Now,
during our research, we worked together with Dr. Gio Legorreta to validate the response of the device for every case. And also we interviewed with medical staff, including the president of Mexico State Neonatology Association, the Dr. Eric Doria. And mainly the feedback was positive. Now, the social impact is divided in 4 main points. First, a correct treatment, savings for the family and the hospitals, reduce in hospitalization time, and an improvement in oxygen therapy protocol. With all of these, we want to prevent the retinopathy in premature babies, which is the first cause of child blindness in Mexico. Thank you. And that's why Baby Breathing is with you since the beginning.
All right, thank you. Okay, we ready for Q&A, Shannon?
Yeah, let me reset the timer. They were under their 4 minutes, just about 12 seconds under. That was very impressive. I'm going to reset for Q&A. Do you
Okay,
want to remove the spotlight so they can?
Sure. Yeah. Judges, who would like to start? Yeah, go ahead, Dr. Lee.
Okay, well, thank you for the wonderful presentation. It's nice to see a lot of new things you have been working on since your last year's work there. So just I think as a continuation then, looking forward, what's your next steps? I noticed you put down there patent pending, right? Do you plan on doing more real clinical trials? And then what are some of the other maybe technical aspects of improvement do you have in mind?
first we have to check to approve a medical protocol as first step. After that, we need to have a final design freeze of our prototype. As you can see, an exploded view of this prototype. You want to put all together in a little package to start testing in a hospital. Also, we need to approve some ethical councils in some hospitals to start this testing.
Okay. Yeah, thank you again. I know, I understand again, your country may have different process in terms of putting this in real people. So certainly all the regulatory requirements, everything, and should be taken into account. But great job, yeah, carrying this through for the past year and making so many improvements in the progress. Congratulations.
Thank you.
Okay, more questions?
Go ahead, Dave.
The software obviously uses the sensor for oxygen level. Could you describe how the software uses the heart rate and temperature sensors inputs?
Did you ask about heart rate and temperature only?
Yes.
Okay, the heart rate we use, and we detect the heart rate using the infrared detecting of a photodiode in order to get how many time passed between the heart rate of the pulses, because each time the pulse of blood passes into the finger, the amount of the voltage detected in the photodiode changes. And for the temperature, we only use a transistor for a temperature sensor to get it.
Thank you.
Okay, Dr. Zhang, do you have a question?
Oh, yeah, I have a question here. I mean, first of all, congratulations, very nice work. And I see you put your pulse oximeter and also ECG signal, temperature sensor, lots of things together. This actually can be a very good example for the course I teach about medical devices design, honestly. So my question is like this. So this device, as you see, is used for monitoring the baby and also to control the oxygen supply, and especially for baby in critical condition. So then you need to kind of, I'm not sure if you think about it, like you're gonna need to think about like how reliable your device can be. And if something goes wrong, is there a way to indicate some part is failing or not? Or do you have any safety interlock to prevent some wrong control? So for example, the oxygen flow very often has to be controlled in a very nice way. For example, you cannot flow too much oxygen to the baby, right? Or you have to make sure if the oxygen has been stopped for whatever other reason, there must be a way to tell the operator, oh, the oxygen is gone, please check, there's some error like that. So do you have some kind of like such design or such kind of idea in mind to implement this one?
¿Cuáles son tus sistemas de seguridad para que no falle? Por ejemplo, el flujo de oxígeno, ¿cómo haces que no vaya a fallar? ¿Cuál es la idea para que no falle eso?
At the moment, we don't have that part, but we taking plan to implement a control model in order of the program, validating in an oxygen sensor to validate if the flow of oxygen is well or not. I hope this answered your question.
Oh, thanks. Thank you.
Okay, thank you very much. Well done. Okay, I think it's time to bring in the next team. Thank you.
All right.
Yeah, next up, we're gonna have Mexitech.
All right, well, they're moving through and moving out and in. I will set the timer to the presentation. We did go over on questions, but the time on Q&A, but I think with the smaller number of teams, I think if everyone's amenable to that, we can add a couple minutes to the Q&A. These are very technical presentations, and I think it's helpful for the judges to have a little extra time. So Mexitech, there you go. They're sharing. And when you begin your presentation, I will begin the timer.
Okay. In Mexico, one of the most important health problems that affect thousands of Mexicans every year are the amputations, which can be caused by different causes, such as vascular diseases, unintentional injuries, the effects of congenital origin or cancer. According to INEGI, in the year 2010, in Mexico, around 785,000 persons do not have any limb. And according to a different information source, for the year 2014, the number of amputees increased to 935,000, which allows to see that the amputation index is increasing every year. According to statistical data, only 1 in 10 people with amputated limbs are rehabilitated, and that only 30% of those rehabilitated know how to use the prosthesis.
This means that 90% of amputees in Mexico have not had access to prosthesis. In Mexico, there is a lack of institutions dedicated to the creation of prosthesis. So about the 1,500 prostheses are produced in Mexico each year.
But all these prostheses are cosmetics, so they do not return the mobility to the patient. Due to this current situation in Mexico, an electronic arm and hand prosthesis printed in 3D is proposed to solve this problem, which offers the same capabilities of a sophisticated prosthesis at a low cost, allowing it to be accessible to all the population that needs a device like this.
Hop Hand was designed 100% by Mexitech.
In this moment, this is our design of the prosthesis. As a control system, we are using some electrical sensors to provide the most natural user experience possible. This sensor obtains the electrical signals produced by my muscles when I flex my elbow or close my hand. So that later these signals can be processed by a Raspberry Pi Pico controller, which interprets these signals and according to the programming code allows the movements of the prosthesis.
Hop Hand has a production cost of $622, which is extremely cheap when compared to the price of other prostheses that exist in the market today. And with this, we are looking to be a cheap and accessible option for people who need prostheses offering the same features as existing prostheses and even better.
Now we are going to demonstrate how the prosthesis function. In this moment, we are going to give a demonstration of how the prosthesis function. Okay. First, I connect the electrode for the sensor in my bicep and in my long flexor muscle. And now I'm going to turn on the prosthesis. I open my hand and the prosthesis open, close, open, flex my elbow, close my hand, open my hand, down my elbow, close my hand, open, close, flex, and down. I open, close, open. And this is the function of the prosthesis with the electrical sensors. And also we have a routine to demonstrate how the wrist of the prosthesis function. In this moment, just function with the sensor, the elbow, and the fingers. In this moment, the prosthesis is function automatically without the sensor. This prosthesis is completely portable. And that is all. Thanks for your attention. Thank you. Okay.
Time's up.
All right, thank you. All right, I guess that we'll start with David Carberry for Q&A.
Are you able to hold anything with that robotic hand?
Sorry, I can't hear you.
Are you able to hold something with the hand, like perhaps a ball or a spoon? Could you hold the device with the hand?
Yeah. The hand can take some objects, but only can take big objects. In this moment, the movements aren't fine to take little objects. Do you want to see how the prosthesis take an object?
Yes, please.
Oh, wait, where is it? Okay. This one is taking the mouse, and I'm going to let the. In this moment, only can take big objects.
Okay, who would like to ask a question next? Go ahead, Dr. Zhang.
Oh, first of all, it's very cool. It kind of remind me the sci-fi movie many years ago, Terminator, right? The guy showed up with hand, robotic hand, very cool like that. So I have two questions. So I think the signal to control the arm comes from your myoelectric sensors, right? So can you explain how those myoelectric sensors are picking up your intention to move the muscles? Oh, hello, I think the screen is frozen somehow. Oh. Hello, is it my part frozen here or?
Yeah, we'll give them a minute to get
Yeah,
back.
we may have lost
Oh,
our.
okay, I just want to make sure it's not me frozen here.
No, no, you're okay.
Okay, thanks.
Yeah, I think how we should work this, yeah, go ahead.
Could you repeat the question? The connection is.
Yeah. It's okay. I mean, can you explain how the myoelectric sensors are working to pick up your intention to move the muscles?
Okay. First, the electrical sensors detect the electrical signals of my muscles, and when I flex my elbow, close my hand, this electrical sense. This electrical.
Yeah, we're having some connection issues with the Mexico team. Perhaps they could respond to that question in writing.
Yeah, no problem.
You want to try the chat? Yeah.
In chat or just send an email.
Yeah, later I'm gonna email them for the question. I think that'll be easier.
Filter, a software filter, read these signals, and then we.
And their bandwidth is our technology is we are at the mercy of our technology. Mexitech, we're going to let you answer that question in writing because your signal did fall during your question, your answer. So if you have a moment to write down what you just told us and send it to us, that'd be great.
How do you want to do it, Shannon? You want them to email or you just use the chat?
If they have the ability to use the chat during the next presentation, that'd be fine. But if they need a little more time, then, you know, we might not be able to accommodate. It might be done with the presentations by then. So however they want to do it. If they have time to respond in chat, they can. If otherwise they need to prepare something else, we can get that to the judges. Dr. Lee, did you have a question?
Yes, I think it may also be answered better through email, but I just maybe quickly here. My main question again is great job. Yeah, I think it looks very impressive. The arm, the movement, everything. So my main question is regards to the design criteria. What should maybe a list of design criteria you have for the arm, and then the main consideration in achieving this. So like all the engineering design considerations you put in getting that hand perform as you demonstrated. So I think our maybe also send email and then they can email back with their thoughts.
Did you understand that, Mexitech, that you will receive 2 questions, one from Dr. Zhang, one for Dr. Lee, that you will have time to respond in writing?
Okay.
Okay.
Yeah, do you understand the questions or do we need to send them?
What?
We'll send them. We will send you the questions in writing.
Okay.
Just to be fair.
Okay.
You might not be able to hear us because of our bandwidth as well. So.
Yeah, so let's do that. Okay, and then so just to continue the pattern with the last team, we will be a little flexible with the Q&A and allow make sure the judges each get a chance to ask a question or 2.
Mm-hmm. Yeah. Okay.
All
right, so I'm going to move Mexitech back into the panelist and move Lana into the, moving Lana to the panelist and move Mexitech back to the attendee side.
Okay,
hello, Lana.
Yes, hi. So I'll be sharing my screen now. Can you see my right?
Yes.
Okay. Okay, so I will start. So hello, everyone. This is Lana Joharji, a recent electrical and computer engineering graduate from King Abdulaziz University. Also, I'm a visiting student at the MMH Labs at King Abdullah University of Science and Technology. Today, I'm going to present our project, which is an adaptive skin for healthcare applications. Be starting with the situation description, the objectives, after that project requirements, but not least system implementation. And at the end, I will play a video to show the project workflow. Starting with the situation description, first, current situation of COVID-19 and the rise of safety precaution standards. Second, patients need to be diagnosed by specialized healthcare staff located in distant places. Third, no contributions in the biomedical field that recreates the palpation technique remotely. So our objectives are build a patient device provided with sensors and one actuator that sense the patient's body physical properties, body curvature, moisture, and temperature. Build an adaptive skin device provided with one sensor and actuators that give the patient's body physical properties feedback wirelessly. Wirelessly connect both devices with total communication delay of 240 seconds. The project requirements are accurately measure the patient's skin, recreate the patient's skin, lightweight, respond with short delay, communicate wirelessly, easily installed and maintained, simple to use, and affordable in price. Regarding both of the devices, two main things were used: software programs such as Arduino, MATLAB, SolidWorks, and COMSOL, hardware components such as 3D printed and fabricated parts, servo and DC motors, sensors, tubes, and materials. So here I'm showing the adaptive skin device. On the left, pin-based shape deformation actuator covered by an encapsulation layer. And for each unit, moisture and temperature actuators are placed as well. For the other device, which is the patient device, so if the doctor pressed his two fingers, so these two units will move down, and on the bottom, sensors are placed as well. Finally, the system implementation. This is the adaptive skin device, shape deformation actuator, sensors, temperature actuator, and this is the moisture actuator. And for the other device, the patient device, shape deformation actuator, and these are the sensors. By this, I would like to wrap up my talk and thank you all for listening. And now I'm going to play the video. Okay, thank you.
All right, thank you. All right, who would like to start with the question and answers? Okay, go ahead, Dr. Lee.
Okay, I'll start. Since this is a little bit shorter presentations here, so if you can just pardon my ignorance here, maybe explain a little bit more, right? What you try to accomplish in here, and in a sense, also like what do you use as? How do you compare? How do you tell the accuracy of your measurement? So a little bit more explanation on your overall design, what you try to achieve, and then maybe the testing, the validation.
So basically what we're trying to do is to do the physical examination wirelessly. So the patient be in a city and the doctor is in another city, and the doctor can do the physical examination wirelessly. Basically, we are focusing on three things: the curvature and the moisture and the temperature. So this is our project is about. For the validation of the data, we did too many experiments. Still, we didn't validate the data accurately because due of the time, but now actually we are working on enhancing the system, increasing the number of units, because as you saw, we just used 9 units. 9 units. So now we are trying to increase the number of units as well. And yeah.
Thank you.
All right, can I go next?
Yeah, go ahead.
Oh, very nice work. So this is basically kind of like an online remote device with the capability to feel the sense of touch from each other. So one of your beginning slides, you mentioned like there are some delays. You said the delay is 240 seconds. I mean, why that long? I'm not sure if that's too long or too short. Could you explain about the time? Sorry.
Okay. So basically, we are using Arduino programming, right? And we are using too many motors, and Arduino works line by line. So we need to have a delay between each and every line, just to make sure that nothing will interrupt the other motor. As well as we are using iCloud to upload the data, and then we need to read the data. For reading the data is fine, but to upload the data, we need to have a delay between each and every how can I say it, upload, because each upload takes like 10 seconds between the first reading and the second reading and the third reading and so on. So this is the delay is because, and in the environment, even we are working on reducing these delays by using maybe another cloud, or by enhancing this cloud by another way. So this is the delay is about, or this is the reason of the delay.
One quick way you could do, you could put all the data into one package, then just send one package right away, rather than doing multiple send one way. Yeah, anyway, thank you.
Maybe this will work, yeah.
All right, David, you had a question?
Yeah, part of it was the 240 seconds. What could you do to reduce that time? And the other part is, are there additional members on your team, or is it just yourself?
No, we're 3 actually. We're 3 in the team. So me and my colleagues.
Thank you.
No problem.
All right, thank you very much. Okay, I think we're going to move on to our last project. Actually, our last project is a senior division, and unfortunately, due to some logistical constraints, the team is not able to attend live, but we wanted everyone to at least see the project. So what we're going to do is show the team video, and then we will be sending the questions and answers afterwards. So I'm going to share the team video at this point. Oops. Just 1 second here. Okay, here it goes.
We are the League of Lesions, and we've chosen to use computer vision and robotics for early identification of skin cancers and other skin abnormalities. Many people suffer from harmful skin diseases. 106,000 people are diagnosed with melanoma each year, and 7,200 die each year, and many more are misdiagnosed. There are several factors contributing to this. Many people do not know what to look for or have access to a specialist. It can be unaffordable, and this allows the melanoma to spread before it's detected. COVID-19 also makes it a lot harder to get diagnosed. I'm Maria. Our goal is to have a computer or robotic system to perform differential diagnosis with the technical term, which is the technical term for classifying the skin lesion. Our goal is to determine if the lesion is good and you're probably okay, if it's bad and you have to see the dermatologist, or if it's okay but you could just keep a watch on it. To perform our analysis, we use the ABCDE rule. A simple analysis to look at the lesion, which we perform with the OpenCV image analysis tools. We evaluate each of these values from 0 to 100, where 0 is good and 100 is bad. And we use decision trees to ask the patient to evaluate certain aspects of the image. To approach the problem, we program a vision-based game to understand how to process images. We took dermatology classes from an OCC instructor, developed algorithms, and evaluated them against our labeled Kaggle dataset of 23,000 images. Our solution is a computer vision-based screening tool.
I'm Nick. To get consistent images and lighting, we need a robot to take the pictures. Our robot is a 3-axis motion system with a camera and writing pens. It also has a board that controls 4 different step motors. We then send G-code over USB to tell the robot where and how fast to move. I did analysis for asymmetry. The symmetric round lesions tend to be good, while odd-shaped ones are bad. My work in the tic-tac-toe game to differentiate X's and O's helped me differentiate asymmetric and symmetric lesions. I calculated the radius based on perimeter and area and compared it to determine how close to a circle the lesion is.
The B stands for irregular borders and blurred edges. We'll look at the same images of Nick's arm. For this, I have 2 threshold levels in the image and determine the change in area. If the area stays constant for large changes in threshold, then the borders are not blurred. If the area changes greatly between the inner border and the outer border, then we know that we have a blurred edge. I'm Melina. I programmed a game called Candyland with a chorus of many different colors that I have to differentiate between. With this in mind, I used the criteria of colors to determine if a lesion was concerning, meaning if there's too much color variation, a lesion may be harmful. To begin analysis, first I pick a lesion, and I mask off the surrounding skin. Then I create several regions of interest throughout the image to take the BGR values. And I analyze the spread of colors from all the regions by their coefficients of variation, which basically measures the variations distribution relative to the BGR mean. If in at least 2 channels, the distribution is relatively high compared to that of the mean, then the lesion's colors are determined to be concerning. D is for diameter. The larger the lesion, the more dangerous the lesion can be. We place the dime on Nick's arm as a reference so we can measure the diameter. First, we identify the dime. We calculate the minimum bounding rectangle, and then take the outer side length. We know a dime is 18 millimeters across, so that means that there are 9.42 pixels per millimeter. The lesion on Nick's arm is 13.7 by 11.8 millimeters.
Hi, I'm Alex, and the final criteria is evolving. Now we'll have the robot take another picture of Nick's arm where we have run the lesion in diameter. We need to make sure that the lighting and the threshold stay constant. Based on Shriya's diameter calculations, we can calculate the area of the lesion. As you can see, it has increased by 5 millimeters. If the changes are significantly different, then it has evolved, which it has.
I investigated dermatofibromas, which are benign and are quite easy to identify. For this, we show a number of examples and ask the patient if it is similar to theirs. This lesion doesn't seem to resemble any of those, so I'll hit no. I study melanocytic nevi, which are known as common moles or birthmarks. Here, we ask if it is similar to one of these. They are identified with smooth edges, consistent color, and have usually been around for a long time, so therefore they're not evolving. This lesion just showed up, so I'll hit no. I study actinic keratosis. These have 3 stages. First, a red pseudo network, then a strawberry pattern, and finally a yellow-white pattern. The best way to identify them is through the yellow and white targetoids. I don't think that makes lesions, so I'm going to press no.
2 additional benign lesions are angiomas, which Alex studied, and angiokeratomas, which I studied. Here we see the septa and lacunae. Notice the light red color of the angioma. If the distinctive pattern you see is probably okay. The darker color of the angiokeratomas can be easily misdiagnosed as a melanoma, though. So I see the distinctive lacunae and septa, so this is most likely an angioma. I'll hit yes.
Even though Nick's lesion looks to be benign, we still need to gather a few pieces of metadata, such as family history and how long the lesion has been there. It looks like Nick will be fine. We're going to recommend that he watches for any growth or darkening. If he was older or had family history of skin cancer, we may recommend that he see a specialist. Any questions?
Okay, that was it for the last presentation. I would like to commend all the teams for their projects. They are a triumph of imagination, hard work, and engineering execution. And I look forward to seeing them in the marketplace in the near future and being able to say I saw them first here at Robofest. The results will be announced at the ROWC closing ceremony on Saturday, October 2nd. All right, so as the Assistant Director of Robofest, I would like to thank you so much for your participation in this online format of Robofest competition using real robots. I'd like to thank all the coaches, mentors, parents, I'd like to thank all the coaches, mentors, parents, students, and judges. Special kudos to the Robofest staff, Shannon and Pam. Who are the winners today? Everyone who learned is a winner. So we are all the winners. Congrats on your efforts and your perseverance. Everyone deserves a round of applause. Thank you so much, and we'll see you on October 2nd at the closing ceremonies. Good luck and goodbye.